Good morning. So you seem to like the news yesterday about the extra points, right? Would you like the news that we're actually going to delete one section? Three, yeah, the next one. So today is the last section of probability distribution. So 4.1 and 4.2. 4.3 has been deleted from your homework. And the reason is it's a couple more different types of probability distributions, but they're not in our curriculum list. They're not required. So I said, let's not do them. So what this means is after today, you'll have tomorrow, which I'm not here, to work on homework and such, and Thursday, we'll work on homework together. I'm going to show you basically how we're going to jump into the next. We're going to use the TI-84 calculator for all of the calculations. I'm going to show you how to do it by hand, but again, we get to some things where it's pretty complicated. And so the easiest way I think you're going to find to do these calculations is with the TI calculator, TI-84. Actually, I've got any other calculator would work well too. So I've got mine ready to go. If you have yours ready to go, you can kind of follow along, which will help you with the button presses. If you tend to get lost, it's okay if you just watch, because this is being recorded as well. And we'll see if maybe tomorrow afternoon, I'll have some time. I can make maybe a few videos on how to use the calculator. But you're going to find it's real powerful. And then when we get to the next section, it's the same way of using the calculator, but with just a different function. Okay, so we're learning about different types of distributions. So, what did we learn yesterday? What was that called? Do you remember? We learned about what kind of variables? What did we call them? Discrete, good, and random, discrete random variables. Also a little bit about continuous ones, but we're not using them right now. So discrete, random. Look at a specific type now, a binomial distribution. When you hear the word binomial, what does that make you think of? Two. Good. We only have two variables. This is for like a yes or no question. There is no maybe. It's just yes or no. It's a success or a failure. There's not in between. So anything we can characterize as a yes or no question, there's a success, there's a failure, that can be done with a binomial. And you're going to see we can take some that don't start off that way, but we can characterize them that way. And they're pretty straightforward in analyzing. Okay, so that's the kind of variable we're going to work with today. We call them experiments. So each time we sort of do a trial, that's called a trial. Each one has it's like flipping a coin, right? Each time you flip that coin, that's a trial. Each time you roll a dice, that's a trial. And then each one has either a success or a failure. So I go back to this all the time, but if it's a 70% chance of rain today, which it kind of looks like that now, what would be the chance of no rain? 30. So if you think in those terms, that's rain or no rain, that's a binomial. It either rains or it doesn't rain, right? And we have a probability that it will rain and a probability that it won't, and those will have to add to 1. It has to be 100%. That's what this gives us. The other that it's independent. So each time we do it, so it's like every day in a row, it's 70% chance of rain. So the probability does not change from trial to trial. Okay, so that's the other important thing. If it does, it's not binomial, and we're not going to look at it, at least not here. What we're going to count as the random variable, remember the random variable has to be a number, and since it's discrete, typically it's going to be a counting number. So for us, the random variable is going to be the number of successful trials. So we go for 6 days, and how many times did it rain? That might be the success. So it's counting how many times we got the success. Flipping a coin, how many times we got a heads, or how many times we got a tails, whichever we call the success. That make sense? Okay, so that's the setup, and that's all we're going to look at today. So just to get us some variables that we use with it, when we talk about the number of times we have of the trial, and we'll look at a few examples that make these a little clearer. We use the symbol little n. So that's the total number of trials. We're rolling the dice 5 times, n is equal to 5. Okay. There's a probability of success. Maybe we want to roll a 3. Probability of rolling a 3 is 1/6. And then Q we use for the probability of the failure. So if it's a 1/6 probability of success, what's the probability of failure? 5/6. Right? They have to add together to give us 1. So we kind of go that route. And then X is the possible number for the random variable. We could have 0 successes, 1, 2, 3, 4, all the way up to n. What did I say n was? We're going to roll it. I can't remember. 5 times, did I say? Again, we could make one up. And so X could be 0, 1, 2, 3, 4, 5. Can't be 6 because we're not doing 6 trials. So, okay, does that make sense? So if we keep that straight, again, we're going to go use a feature in our calculator that will do all the calculations for us, but we'll also look at how the probabilities are calculated because we know somewhat how to do these probabilities. So here's one, and this one we just want to identify, is it binomial or not? So a certain surgical procedure has an 85% chance of success. The doctor does a procedure on 8 patients, and the random variable represents the number of successful surgeries. Is that binomial? Yes, no, or maybe. Feels like it, right? We have a chance. We have to make an assumption that each surgery is independent of success, but that sort of seems to do it. There's 8 patients, so he's doing the surgery several times, and it's either going to be successful or not successful. So there's only 2 outcomes. So that is a binomial experiment. What would be the value for n? How many trials? 8, right? They did it 8 times, so 8 people. What would be the value for p? 85%, or 0.85. That's we'll be using the decimal version. What would be the value for q? 15, the complement, right? Good. And then what would be the values that we could put in for x? X is our random variable. Could we put 9 in for x? Could x be 9? No, because there's only 8. So it could be 0 to 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's all the values x can take on. Okay? And there it is. All there. Okay? That's binomial. And what we do is we're going to get that distribution. What's the percent that only 0 successes, 1 success, 2 success, 3 success, and we'll see that distribution develop as we go. Okay. How about this one? A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select the marbles from the jar without replacement. The random variable represents the number of red marbles. Is that binomial? Somebody said, what do you feel? No, it doesn't feel like it. Why not? What's that? There's multiple outcomes, but if we count it just as red or not red, that'd be okay. But there's a problem here. What about the probabilities for each trial? Since we're not replacing it, what's happening to the probabilities? They're changing on us, right? It's a conditional. So that's the problem. It's not binomial because of the changing probabilities. And you're right. Usually when we look at these, you get a red or you get a yellow, or so there's multiple outcomes as well. We could fix that one, but we can't fix this not replacement that the probabilities are going to change on us. So it's not binomial. It could be something we're interested in, but it's not binomial. So we're not dealing with it today. Okay. And that's part of the thing is as we get more of these distributions, you have to be able to identify what kind it is so that you're using the right tool. Okay. So here's the formula for the binomial calculation, where remember x is the total, is the and we'll go through one, we'll walk through one, but you're getting the probability of a success raised to the x power, how many successes, the probability of failure raised to n minus x, which would be the number of failures, and then we've got to multiply by this, and we'll see why, because the next example kind of brings it out. But we're actually I'm not going to have you use this. In the past, that's how I would have done it, but we're going to go in and use the distribution features in your TI calculator, which has this built in. Okay. Again, n is number of trials, p the probability of success, q probability of failure, and so forth. So let's take a look at this one. And I think on this one, I'm actually going to show you how we can calculate it. Rotator cuff surgery. What's a rotator cuff? All right, you guys know. Yeah, my brother just blew his, so he works on the docks, and so he's off. It was workman's comp at least, but fortunately, 90% chance of success. So if he has to go into surgery, that's the good news for him. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Exactly 2. Is it binomial? Yeah, it is, right? What's the probability of success? 90%. What's the number of trials? Be careful here. 3. 3 is the number of trials. 2 is the random variable, is the x value. So in this case, n will be 3, x will be 2. Exactly 2, right? I'm going to show you, I think this is where I'll go. So to calculate these, notice on your calculator above there's a red key. Or let's see, what color is your key? So it's a clear key. It says VARS, VARS, and above there it says distribution. That's the key we're going to use. So it's a shifted key. So I'm going to go second VARS, which gives me the distributions. And notice these are just all the different types of distributions. The normal's at the top. That's what we're going to do next week. So as you get this down, you're just going to come and do a different one next week. So, but it's going to be very similar. I don't see binomial. Where? Maybe it's lost. No, there's an arrow. There it is. It's way down here, right? There's 2 types of binomial. And we're going to, so there's PDF, which is a probability density function. That gives us a probability for a single value. That's the one we're going to use right now. CDF is cumulative, right? Cumulative distribution function, okay? Cumulative. And so that one, when we use that one, that's going to give us the percent for a number or below. So if we wanted 2 or less, we would use that one. But we want exactly 2, so we're going to go up and use this one. Now, I was practicing last night, but I kind of forgot, but I think I got it right. We have to give it 3 numbers, and we have to use them separated by parentheses. So the first one we have to give it is n. So what was n? 3 trials. We have to, and then we put comma. We have to give it the probability of success. In this case, it's 90%. Is that yeah, that's a comma. We do 0.9 for the probability of success. We put a comma, and then now we need to tell it the value of x. How many successes? Exactly 2. We put that in, and we put a equals, and we put an enter, and magically it calculates it for us. That's all we're going to have to be able to do. You just have to remember NPX. Okay, you put it in, and I'm going to show you. We'll have the PowerPoint do it by hand as well, and we're going to see that it matches up with this. We're going to do it two different ways to kind of verify to us that this is giving us the correct answer. Okay, so far so good. Questions? I got stuck.
I have a question.
Yes.
So when they're showing their work, if you ask them to show them the work, do they have to write out what the command is on the calculator? Or
I don't ask to show work. I ask to interpret the answer, though. Okay, so be able to interpret what your answers mean. Yes. Oh, yeah, okay. Yeah, so if you, yes. Think of it, it's going to give us each individual probability, or the cumulative probability. I had to look it up last night because I know there were two of them, but I couldn't remember which did which. We good? Okay. What I want to show you, though, is how you could do this. And again, you have enough from what we've done with probability before. So there is this way of doing it. And remember our last test, we had something like this. And Mrs. Lee showed us how that's how she worked it out with a tree diagram. So the first surgery, you're either successful or not. Something based off of that. The second's either successful or failure, success or failure. And the third surgery, we have these. So remember, it's two different things. So 2 times 2 times 2 is 8. There's 8 different things that can happen. So these are all the different things. And then to calculate the probabilities, we do this thing where each trial we multiply by their probability. So success is 9/10 or 0.9, 0.9, 0.9. We get that. Probability of 2 successes is 0.9 times 0.9 times 0.1, right? And there are three different outcomes that have 2 successes. And so we can take that 81 over 1,000 for each of them, add them together because these are OR probabilities, or multiply by 3 because they're the same. Notice that 0.243, same thing we got. But does that visual be a little bit more convincing that this is the right way to do it? Okay. So if you think in terms of tree diagrams, what would be the problem with using a tree diagram, though? 5, 6, 7, 8 trials, 100 trials. You try to do that with it? No, it's not going to work very well for if you get much more than the 3, right? We still, each one is a success or failure, so it's not too bad. But beyond 3, it's going to get messy and probably hard and a lot of calculations. Again, we can do it here. But we do this to emphasize that this is the answers we're getting are accurate, okay? We could also use the formula. And again, sometimes it has meaning. Okay, this calculation right here is sort of the formula for 3 choose 2. So you could just use that on your calculator. You would get the number 3. Notice this is the probability of a success, 0.9, 2 times. Probability of a failure, 1 time. And then we're multiplying, it ends up that there's 3 that come out. That's what the formula shows us. And we multiply the formula out, and we get 0.243. Now, that's, if we're just thinking of the mathematics of it all, maybe that's what we would practice doing because that feels more like math, right? We're plugging in numbers into a formula. But we're doing statistics, and what is statistics for? Program, and they makes you do it, so you just come and you do it. right? That's usually why I went to class. They told us. But the reason we want you to do this, statistics is about taking the data, analyzing it, and being able to make good decisions. Okay. So what we need to do is it's more important, or it's as important, that we understand what those values mean. The more important thing is that we realize the probability of getting exactly 2 successes is about 24%. Right? And I want to get the whole distribution. So there's multiple ways to calculate it, but if we use this tool, we're going to get those values, and I believe you're going to get them consistently right, and you're going to build a deeper understanding of what you're getting. Okay. Now let's take one that doesn't look like binomial, and let's see how we can make it binomial. And again, we're going to use our calculators, which will give us correct answers relatively easily. We have to follow through. We have to know 3 things. N, how many trials? We have to know the probability of success, and then we have to know what X value we're looking for. I see more than 2, right? But what they're going to do is they say 6 adults who participate in the survey are randomly selected, and they are asked whether they go online several times a day. Notice that's one of the answers. So they're going to count this as a success if the person says yes. If they're one of the others, they just say no. So notice, even though there's multiple answers on the survey, they're now, did they answer yes to this particular one or not? So we've turned it into a binomial. Does that make sense? Okay. So they're just asking, did you go several times a day? Yes or no. Construct a binomial distribution for the number who responded. They go online several times a day. So first of all, let's set this up. What is our value for n? How many trials does this thing have? 6. We picked out 6 adults, so that's our n. What's our probability of success? 48 from the survey. Probability of not having a success, 52. But we're not actually, with this calculation, we don't need that. But and then, what do we want to know? What is x? Well, possible values are 0 to 6. We want the whole distribution, so we want to calculate all of them. Okay, so I'm going to, we'll go to the next page. Right, here's our setup. P is this, here's Q, N is 6. We want to calculate all these values. We're going to use the calculator for all of these. Again, remember how to get there. Second distribution. Have to go down here. I'm going to show you a little trick, and we want the PDF, not the CDF. CDF is going to be cumulative, right? We want the PDF. What is our value for n? 6, comma. What's our value for p? 0.48 or just 0.48, however you want to do it. And then we're going to calculate each x value, so we'll start with 0. And it gives us 0.01977. So if we round it to 3 decimal places, that's about 0.02. Over here, we're going to have the PowerPoint use the formula. Notice 0.48 to the 0 power, no successes. 0.52 to the 6 power, 6 failures. And they have to use this combination because how many ways it can be done. But they got the same value we received, right? So you could use the formula, or we can use the calculator. Which one would you like to use? Me too. Okay. Like the hard way? You do the easy way, the hard way. I don't care. But watch. We need to do the next one. I'm going to show you a little trick. If you arrow up and highlight this and hit enter, it's going to bring it down. And now we just go back and change the 0 to what? Arrow Doesn't work on that.
You guys are not able to arrow up, and you guys are going to hit second, enter, and it'll put in your last entry and edit.
We got somebody smarter. Average bear here. Second, what's that second? Enter, it will bring it back. Scared there, I didn't know what to do. But now that it's there, you back arrow and do 1, okay, and then enter. We've got that calculation. Actually, I like that way. I'm going to see if my way, that's a little bit easier than arrowing up. Okay? Notice we match the same way, the same number as the calculation. Let's try that. Second, enter. Oh, beautiful. It brings the last one down. So you don't have to go through all these things. And then we just back up and put in 2. And we get an answer. Or we could use the formula. Again, formula, we could do the same thing and just change the variable, the exponents, I suppose. But, okay. Second, enter. Change the 2 to a 3. 3.11. Oops. Okay. And actually, I guess I could just hit through all of these. These are all the calculations we would make. But notice we can do just simply with the calculator. Second, that back, and changing that last number there. Okay. Okay. I think we might be able to do that. So when we have our work day on Thursday, I'll bring my cables, and maybe if you want yours updated so you can arrow up, we can do that. I think we can get yours updated. If not, you don't have to. Does that make sense though? We can calculate, and that's what I want you to remember, because you're more likely 6 months from now to remember that, oh, there's a feature on my calculator that does it, than to remember the formulas, right? And that's what I want you to be able to do, is I want you to be able to do this 6 months from now, 2 years from now, when you start to do some sort of research project. And you got a yes/no question, and I know how to analyze those things with this tool. And if you don't remember, Google it, and there's lots of videos. That's how I did it last night. Is I knew there was a feature, Binomial, TI, and a video comes up and shows me. Okay. All right. So far, so good? Great. So then we've got our distribution here from 0 to 6. What I want to show you is we're going to use the other one, the CDF. If I do the CDF of 6, it means 6 or less. What should I get? Since I've only got 6 trials, I should get 1, right? Because that's everything. So I'm just going to go second, distribution. Since it's a different feature, it's not the PDF, I'm going to do the CDF. I put in the same values. I put in 6 trials, 0.048. Oh no, 0.4. Well, 0.48. And I'm going to put 6. And in this case, it's not exactly 6. It's 6 or less. That's what the CDF is, cumulative. And notice it's going to give me the answer of 100%. That's everything 6 or less, right? And that's because it added all these together. And we're going to get 1. Okay? We good? You good here? How about back here? It makes sense? Okay. So now is the one they asked us to do technology. Okay, think about math because we can finish this up and then it'll be all there, right? Okay. With this one, 75% of US adults experiencing digital device fatigue. How many of you have digital device fatigue? Yeah, tired. I got to put them away, right? Okay. 75% of adults, what is it? Exactly 66 are experiencing this. All right. Do we use PDF or CDF? PDF because we want exactly 66, not 66 or less. Again, sometimes we still have to remember where it is, the distribution. Actually, if you arrow up, you might get there a little quicker because it goes from the bottom of the list. It shows you also the other ones that we have. PDF, RN is 100 because we got 100 people. Our probability of a success, 0.75. And then our X value is 66. Now, sometimes, I mean, if you're putting this in the formulas, remember that would be like an exponent of 66. And this is set up. It tells us about 0.011, so 1.1% for exactly 66, remember? That kind of makes sense that, yeah, if you got 100 things going. Okay, so we can get these values, and that's the two features we need to use. Okay. How much time? Okay, good. I want to get at least, okay. Now this one, survey found that 22% of US adults say that economy, unemployment, jobs are the most important problems facing the US today. You randomly select 4 adults and ask them whether the economy and unemployment jobs are the most important problems facing the USA today. So to them, it's a yes or no question, right? 22%. How many people did we ask? 4. And then the first question, we want the probability exactly 2 of them responded yes. Again, we could bring down our binomial if you want. You could do second, enter. We have to change a lot of stuff. Change this to 4. Probability of success is 0.22. And we want exactly 2. So I'll do delete and put a 2. About 17.6% or 17.7. Actually, we could write it here, 0.177. Now we got to get a little tricky here. The probability at least 2 of them respond yes. At least 2 means how many? 2, 3, or 4, right? So 2, 3, or 4. We don't have a feature that will give us that. So one way to do this is we could calculate 2, 3, and 4 and then add them together. If we wanted to use the cumulative one, what would we have to do? This one is a little problem solving. At least 2. Remember what we did when we had something that like wanted at least 1 or something? We didn't directly calculate what we wanted because there was a lot of calculations. We calculated what we didn't want, and then we subtracted from 1. What if we calculated less than 2, which would have been 0 and 1, right? And then subtract it from 1. Would that give it to us? Yes, it would. So we're going to, with this one, we're going to use the CDF. But remember, the CDF is less than or equal to, so we can't put the CDF of 2 because that would give us 2, 1, and 0. We want the CDF of 1. So I'm going to go up here, arrow up to the CDF, and it's still 4, comma, 0.04, or but I'm on the wrong problem. 0.22, 0.22. And we want, since it's the cumulative, we want to put in 1. So this is going to give us 1 and 0 added together, 0.7877. And then we have to do a little calculation, 1 minus 0.78. We'll round it to 3 decimal places. And so that gives us 1 minus the answer. Notice the answer's down here, second answer. So our answer is going to be 0.212. But look at that. Fewer than 2 of them responded yes. I should have asked that one first, because we didn't we calculate that? Fewer than 2 of them is 1 and 0. Oh, that's that one. So we didn't waste anything. We actually already got our answer, right? So that would have been definitely just a cumulative. You have to remember the cumulative to be that number and below. Does that make sense? You want to see how much work it would have been with the formulas? This one's not so bad, right? Probability of success, 2 successes and 2 failures, and this is that's the same number we got, right? 0.177. But watch this with the at least 2, how they calculated it. They got 2 to 3 using the formula, and then they had to calculate that and add them all together. But look what they got, 0.212. Same thing we got using the cumulative, but taking it 1 minus, getting the complement. Does that make sense? Okay, so some of these you're going to have to, a little bit of problem solving. Remember, solve for the complement and then subtract it from 1, and it's going to be the easier calculation. But that's really cool. That's all we have to do with these. And then the last one, the way they did it with the formula, again, 0 successes, 1 success, and then they add them together, but they got the same number we did with just using that CDF, the binomial probability distribution for a CDF, 1 or below. Okay. What do these numbers mean? What does this 0.78 mean? It's a percentage, right? Percentage of what? Percentage of what happened? Fewer than 2 respondents said that they are in that group, right? Because it's a 50-50 thing anyway, almost 50, 48%, right? So we have a 78% chance that 0 or 1 people are not in that group.
Okay, well, I kind of find it helpful to kind of write down the numbers, like 0, 1, 2, 3. Was it up to 4?
Yes.
So if they say like at least 2, I know that I want this part over here. But your calculator only gives you guys from 0 to that. So you guys need to do 1 minus what the calculator will give you. So for me, I find it helpful to write down the numbers and figure out what am I looking for, what will the calculator give me, and then I go from there.
Good. Yes. Yes.
And
when I'm working, I do them down too. So that's the kind of things you have to know is write down what we're doing. This one we're not going to do, but I just want to show you an older way of doing it without the formula to show you that we're using technology. Is it that we're just cheating or getting it easier? The other way to do this sort of thing, okay, we'll just look at this real quickly. 5% of workers commute to their jobs. Randomly select 8 workers. What is the probability that exactly 3 of them use public transportation? In the old days, 40 years ago, before we even had these calculators, uh, it was even hard to do those calculations with the formulas. So what they did, they would have somebody else do the calculations and make a table. Can you see this? So this table set up, if it's a 5% probability of success, you've got your in here and then your numbers here. So it's basically got the distribution for you. But you'd have to go down the list and then you could look it up. But does anyone see a problem with a table like this? Numbers could get mixed up. And what else? It was great if it was exactly 5%, but if it was 6%, could we look it up on this table? No. We could go to 10%. So there's a lot not on here. We could maybe estimate, but at the same time, but this is a way. And when we get to the normal curve, that's a way that's still taught is here's a table of values, look it up, on the table. And I'm going to favor using the calculator. And part of this, one of the person that I worked with over in Scottsdale Community College, he was a high school teacher for 20 years. He came to us and he set up our statistics class, and he would only use the calculator. So that's my influence. Am I right? Is he right? I don't know. But just letting you know there's multiple ways. If you're struggling with using the calculator, if it's not seeming real to you, maybe we can work with calculation. Sometimes that helps. But I also think that a lot of times having that calculator to calculate it gets you moving quicker and gets you to understand exactly what we're doing in statistics, which again is more important than manually being able to calculate everything. Computers can do that, but computers don't necessarily really understand what those numbers are. They give us the values, but ask your TI, what does this mean? What does it tell you? It doesn't even talk, does it? Okay. Let's see, where do I want to go next? How much time do we have? 5 minutes. Let me do this. I don't want to rush this one because I'm going to show you how we can do this, but what we're going to get to, we'll pick up this on Thursday. But I'm also going to provide a little bit of I'll do a few of the homework problems on video, sort of as a flipped. So I'll do those this afternoon. I'm going to encourage everyone to do. I know some of you are trying to make up some other homeworks, which is great. Remember, we had through that week. But if you can work at least on a few of the problems, I'm going to give you a few examples on a video to work through at least some of the 4.2. Remember, we don't have 4.3, so we're getting done a little early. And then on Thursday, I'll come back and I'll show you this one. And this will lead us into being able to actually get the mean and the standard deviation as well. Okay. Yeah.